everybody's favorite.
Since we only have 30 minutes, I think. I did the 30-minute one.
Yeah.
Could we do one in each section?
Sure.
One problem?
Sure.
Cool. And so
Yeah, I'll let you pick.
Okay. I need to open a Google Doc because I can't write.
Well, you don't need to write. You just need to tell me which problem you want to do.
Okay. So, let's do number 3.
Okay. All right. One of the tricks about, here, let me change that color. That's a horrible color. One of the tricks about proving trig identities is if you can't do it, as a last resort, change everything to sine and cosine.
Okay.
Well, most of this thing's already in sine and cosine, right?
Right.
So that's almost certainly the way we want to go here. So the only thing that's not in sine and cosine is the tangent of x. So what is the identity that takes it into sine and cosine?
The Pythagorean identities?
No, these aren't squared. The Pythagorean identities work when they're squared. So for this one, how about the quotient identity?
Yeah. Yeah.
What is it for tangent?
Sine of x over cosine of x.
Now, the whole left side is in sine and cosine. The whole right side is in sine and cosine. Is all I need to do is perform a little bit of algebra on that. And I'll bet it turns into the right side.
Yeah.
Okay. So where do we start in performing our algebra?
So
always start with the smallest, most complicated part.
So yeah, the bottom.
Yeah, well, we need to perform that operation. What is 1 minus sine over cosine? When you are subtracting fractions, what do you need to do?
Have a common denominator.
Okay, so here's what I'm going to write this separately over here on the left, just so more understandable. So what's the common denominator? When I do 1 minus sine x over cosine x, what's the common denominator? It's cosine x.
Oh, okay.
That doesn't change. But what goes here? What's going to make that thing equal to 1?
Cosine over cosine?
Yeah. So that cosine x goes there. Now, my whole goal here is to transform that without changing it. So far, I have not changed it. It's exactly the same. The only thing is I can now subtract those two fractions because I have a common denominator. So that whole thing goes over cosine x, and then the numerator is cosine x minus sine x. Okay, so that is that right there.
Okay.
Okay, now how do you divide fractions by another fraction?
Leave. So I learned leave switch. Or leave dot flip.
Flip and multiply instead of dividing. You flip the bottom and you multiply. Okay?
Right.
So that's going to give me, if I look at this whole thing right here, it's going to give me cosine x times this over here flipped.
So,
And it's like that. In other words, I'm multiplying cosine x by the flip of that.
okay.
Well, that gives me cosine squared of x. Actually, no, it doesn't. One of those cosines, excuse me, hold on. Cosine x minus sine x. It does give me cosine squared of x. Okay? So this whole thing
Right.
I have in square here becomes this. So let's replace it.
All right.
Let's replace everything we have there. And now I've got cosine squared of x all over cosine x minus sine x. So that's where we're at this point. Now let's see if we can make that look like this thing at the right. Well, what's the next thing I can do?
You can.
I've got a denominator here that is the negative of that.
Yeah.
So I can live with that denominator. If I want to switch it around and make it sine x minus cosine x, I just have to multiply everything by minus 1. Okay? But I still have another algebraic process that I can do. In other words, I have to take that and subtract that fraction. What do I have to do? When you're subtracting fractions?
So, have the common denominator.
Okay. The common denominator. I'm doing this the long way. I don't know. When you're proving trig identities, a lot of times you can have different paths.
Okay.
So what has to go there is cosine x times cosine x minus sine x, right?
Mm-hmm.
In other words, that makes it the same as that.
Right.
What goes over here is the same thing that was there. Okay, so now we've got that. Now we have a common denominator here. Let me go up to the left. Start writing. On the left, our common denominator is cosine x minus sine x, right? In other words, it's that and that. Now, let me distribute. On the upper left, I'm going to end up with a cosine squared minus cosine sine minus cosine squared. So the cosine squared disappears, and I end up with minus cosine x sine x. So that's what I get when I combine those numerators.
Okay.
And now we're getting really close. First of all, I can switch the order of the numerator to make it sine x cosine x without doing anything. Still that negative sign there. Okay.
Okay.
And now the only difference between that and that is the denominator. So if I switch the order of the denominator and make it sine x minus cosine x, then I can do that by just multiplying the numerator by -1, which gives me bingo.
Cool.
That was a hard one. There were a lot of steps there.
Yeah.
That's much harder than median. Okay? Although what made it easy was that they started out with almost all sine and cosine. The only term we needed to change was that. And once you get it all into sine and cosine, you can almost always work it out. I mean, there's a lot of algebra, and you can see that tough algebra is really the key to doing these.
Yeah.
It's all this difficult algebra where you're subtracting a fraction from a non-fraction. You know, when I was subtracting 1 minus sine over cosine, that's subtracting a fraction from a number. And then I'm subtracting this from cosine x. That's difficult. So the algebra is the tough part here. As long as you know your identities. Okay? Now, one thing you should know is that there are no real-life problems where you have to prove identities. There is one purpose for this and one purpose only. You know what it is?
No.
Get you to memorize your identities.
Okay.
There's 11 basic identities. There's only 11 that these first 6 problems all deal with. And that is those 6 reciprocal, 2 quotient, and 3 Pythagorean.
Yeah.
Between those 11 identities, you can prove all of these. Well, I may have to take that back. I see a sine of 3x. So we may need a multiple angle identity. And I see a tangent of a sine of 2x. So I'm not sure about that. You may need a few more identities. I assume you've had the double angle identities and the half angle identities?
Yes.
Okay.
The double angle for sure.
The most important ones to remember are those first 11. The 6 reciprocal, the 2 quotient, and the 3 Pythagorean.
Okay.
That'll get you through most problems. Okay. In fact, I'll bet it'll get you even through some of these problems. I'm not even sure how to tackle 4. But, all right. Let's go on and try solving some trig equations.
Okay.
Okay. This is different. What we know on the first 6 problems is that they're all identities. We're not solving for theta. We're not doing anything but proving the left side is equal to the right side.
All right.
Number 7 is different. This is a trig equation. There are plenty of those in real world problems that have to be solved. In other words, this could be an equation you come up against when you're trying to solve a real-life engineering problem. And we need to solve for x.
Okay.
So, what's the first thing we can do?
Square.
No, think of it as a polynomial equation. In other words, think of it as if I'd have said x plus root 2 equals minus x. What would you do as the very first step?
Add x?
Yeah, you would gather like terms, right? Not only would you gather like terms, you would put all terms with x on them on one side, and you'd put everything else with numbers on the other side. So you'd end up with 2x equals minus root 2.
Yeah.
And then x would be equal to minus root 2 over 2. Well, trig equations are exactly the same. They really aren't any different. Do the same process. What do you get?
So 2 sine 2x? Or okay.
Well, there's a difference. This is definitely 2. In other words, that's an apple, that's an apple. And I'm adding an apple to both sides of the equation, so I get 2 apples.
Okay.
It's not squared. I'm not multiplying them. Okay, and then I'm going to put my number on the other side. Now, the first thing I have to solve for is the sine of x before I can solve for x. So what's the sine of x equal to?
Negative root 2 over 2.
Okay. Which makes x what? What angle?
Sine.
In other words, x is an angle. And we know that the sine of that angle is root 2 over 2. What's the first quadrant angle where that's true?
Pi over 4.
Okay.
Or, yeah.
No, you're absolutely right. But that would be if it was a positive root 2 over 2. This is a negative.
Right.
So what quadrant is sine negative in?
The fourth quadrant.
So there's one answer. Well, let's talk about that for a second. What I did was I took the inverse sine of negative root 2 over 2. If you do that in a calculator, you will get a negative angle. Always.
Right.
Now, this happens to be the same as 7 pi over 4, which is coterminal to it.
Right.
And that's the positive angle that it is. But they didn't list any domain here. Okay? So I assume they mean all real numbers. So what other quadrant is the sine negative in?
The third.
And that angle would be 5 pi.
5 pi over 4.
Okay? So here really are two answers. If I want to talk about positive angles only. Now, because they did not specify a domain, most of the time they'll tell you that it needs to go between 0 and 2 pi. Right?
Okay. Yeah.
This would be only two answers. Okay? In other words, that's your third quadrant answer, and that's your fourth quadrant answer, which is the only two quadrants where sine is negative. However, they don't say that when they say solve it. They just say solve it. So it's not just 5 pi over 4, it's all coterminal angles of 5 pi over 4. Well, how do we write that? I presume you've had this. Tell me if you've had this or not. Plus k times 2 pi. Or n times 2 pi. Or 2 pi n. And what k is all real integers. All positive and negative integers.
Okay.
When k is 1, then we've got 13 pi over 4. When k is 0, we've got 5 pi over 4, right?
Yeah.
Well, when k is 1, we add another 2 pi to that, which is 13 pi over 4, which is also an answer that satisfies this problem down here. Another answer is to add another 2 pi to that, which means when k is 2, And now you have 21 pi over 4. And the same thing applies to the fourth quadrant angle. And believe it or not, this is kind of the way you have to write it. You have to write it as two different things. There's no way I can write this as one thing, one row only. Okay. And notice that when k is minus 1, you get that minus pi over 4 in the second one. In other words, if you look at this one and you plug in k is minus 1, you get negative pi over 4, which is the answer your calculator gave you. But remember, the calculator only gives you the principal quadrant. It does not give you both quadrants, ever.
Right.
When you take the inverse sine of something, if it's a positive argument, you're going to get a first quadrant angle. If it's a negative argument, you're going to get a fourth quadrant angle. And it's going to be negative. They're going to call it a negative angle. And same with tangent. Cosine's a little different. When you use your cosine to do an inverse cosine, or when you use your calculator to do an inverse cosine, positive arguments give you first quadrant angles. Negative arguments give you second quadrant angles. So you don't get negative angles when you do inverse cosine. You only get that with sine and tangent. Okay. So this would be the correct answer. And k is just a positive, it's an integer. Meaning it can be positive, negative, or 0. It can't be a fraction, though. It can't be 1/2. But it's all the integers from negative infinity to positive infinity. So this answer is an all-inclusive answer for all numbers on the number line.
Okay.
Okay? Now, I'm assuming that's what they meant, because normally, if they didn't mean that, they would say x is between 0 and 2 pi. And then you only have to worry about the unit circle answers.
Right.
But if they don't if they don't specify a domain, and they don't, I assume you're not supposed to use your calculator here, right?
Right.
Correct, yeah, because all of the arguments are numbers that we should know. In other words, we should know that root 2 over 2 is a 45-degree angle.
Okay.
All right. We got 5 minutes. Let's scroll down and do a sum or difference. But all of these trig equations, just treat them like you would a polynomial equation.
Okay.
Now some of them, before we go on, there's some things I need to address here, because these are not trivial at all. Solving that is a quadratic. It's what I call a quadratic in disguise. Because most quadratics, you're looking for something like this. Well, or that rather. Well, this is called a quadratic in sine. Just like this one is called a quadratic in x. So if I want to solve this, I'm going to factor it, just like I would a polynomial. And I get 2 sine there, and I get sine there. In other words, I split up the sines. And I get minus 1 plus 1. If you multiply those two together, you'll get what we started with. And now I can solve it. In other words, either 2 sine plus 1 equals 0, or sine minus 1 equals 0? Well, this one's pretty easy to solve. Sine of equals 1. Let's just restrict our answers to the unit circle for the moment. Where is the sine equal to 1?
Pi over 2.
So that's one answer. And then if you solve that one, what do you get? Sine x equal what?
Sine of negative 1/2.
Where does that occur?
Quadrant 3, which is 7 pi over 6.
That's the third quadrant. How about the fourth quadrant one?
11 pi over 6.
Good. You're pretty good with the radians. I'm impressed. And if, once again, had they restricted the domain to the unit circle, that would be your two answers. If they're not restricting it, then your two answers are going to look like this. 7 pi over 6 plus multiples of 2 pi. Or 11 pi over 6 plus multiples of 2 pi. So this would be your answer.
All right.
Okay?
Cool.
All right, let's see. We only have a couple of minutes here. Do you have any questions about any of the others, how we would even start them or begin them? There's a lot of material here. We could really have used another half hour probably to go over this. Solving these triangles can be a little tricky, especially if you have the ambiguous case of the law of sines. This problem here, what are we going to use to solve that?
So that would be
we don't have a triangle that tells us with a 15-degree angle. So we can't use our two basic, 30, 60, 90, and 45, 45, 90 triangles to solve this problem. But
right.
what we can use is our half angle formula. In other words, the sine of 15 is the same as the sine of 30 over 2. Right?
Yes.
And what is the identity for the sine of theta over 2? I think it's that. Want me to look it up, or do you have it in front of you? Either one plus or one minus. We'll assume it's this. But can you see how this benefits us? In other words, theta is 30 degrees. It's not 15. Remember, I wrote it as 30 over 2, which makes theta 30. And we do know this, the cosine of 30. That's one of our common angles. So this would be plus or minus, and we'll get to that in a second. 1 plus, what's cosine of 30? It's root 3 over 2.
3 over 2. Yeah.
All divided by 2. Now we can simplify that into a radical format just easily. Just again, algebra, you have to add 1 to root 3 over 2. But this question of which one we choose there, which one are we going to choose, the plus or the minus?
The plus.
Because we know it's a first quadrant angle. 15 degrees is in the first quadrant. Sine has to be plus.
Yeah.
So we get rid of the minus, and whatever that comes out to be, and here I can do that pretty quick. It's 2 plus root 3 over 2, all divided by 2, which is 2 plus root 3 over 4. So it's 2 plus root 3 over 4. That's assuming I got that sign correct. If that's a negative sign, then it's 2 minus root 3 over 4. But you're going to have to look up what your half angle formula is. For some reason, it's very close to cosine of theta over 2. Cosine of theta over 2 is 1 minus, I believe. I believe sine is 1 plus. But you can look those up when you're doing your homework, at least. And you may not be able to on a test, but this gives you a good idea of what you need to memorize. In other words, this is one of them you need to memorize, that half angle formula. I presume that when you take your test, they don't give you these identities? They don't give you a separate page?
No, I don't believe they will.
Okay. Okay. Then you got to memorize them. Not that many to memorize. You probably know your first 11. The sum and difference, fairly easy to memorize. The half angle is okay. The double angle is easy to memorize. Those are the three you need to add to your repertoire, are the sum and difference for sine and cosine, also the double angle for sine and cosine, and the half angle.
Okay.
Okay. Demetrius, good luck on your quiz. I'll talk to you again, and I'm available. This is a lot of material to cover in a half hour. Hope your test isn't tomorrow, but I've got time over the next few days if you need another session to cover the rest of the material. Okay?
All right. Sounds good.
All right. You have a good rest of your day, and I'll talk to you next time.
Sounds good.
Bye-bye.
Bye.